Welcome to Kognito Key. I am absolutely thrilled you're tuning in today. Let's dive right into this explainer on how tiny impurities inside microscopic crystals actually power our entire digital world. From your smartphone to the internet itself, it all starts right here with the very foundation of modern electronics.
Before we split our discussion into the two main types, we really have to understand the foundation. An extrinsic semiconductor is simply a pure or intrinsic crystal, like pure silicon, that has been deliberately doped. And by doped, I mean we've injected it with very specific impurity atoms. We do this to completely change its electrical properties and make it highly active. You see, pure silicon on its own isn't all that useful to us, but doped silicon, that changes absolutely everything. Let's kick things off with our first category, P-type, the acceptor, the power of the positive vacancy. So a P-type material is created when we add group 3 elements from the periodic table directly into our pure silicon. We are talking about elements like boron, gallium, or aluminum. In the world of physics, we call these trivalent impurities. Tri meaning 3, which refers to their valence electrons, and that number 3 is the absolute secret to this whole process. Here's the math behind it. Pure silicon has 4 valence electrons in its outer shell, but our impurity, let's say aluminum, only has 3. When they bond together to form a crystal lattice, they are fundamentally mismatched. That bonding leaves an empty space, a literal vacancy right where an electron should be. In electronics, we simply call this missing electron a hole. The crucial point here is that this extra hole acts as an acceptor atom. Since it's missing a negatively charged electron, the hole itself actually acts as a positive charge. In a P-type material, these positive holes become what we call the majority charge carriers. They are the primary agents responsible for conducting electrical current through the material. Energetically speaking, all of these empty, positive holes create something amazing. The Fermi level of the material drops to sit very close to the valence band. This means electrons from the surrounding material can effortlessly drift right into this acceptor energy level. When they move to fill one hole, they leave behind a new hole, creating a cascading flow of positive charge.
All right, now for the flip side, N-type, the donor. Let's look at the power of the extra electron.
To make an N-type material, we form it by doping the pure silicon crystal with pentavalent elements. These are group 5 elements from the periodic table, such as phosphorus, antimony, or bismuth. Remember how trivalent meant 3? Well, pentavalent means these atoms bring 5 electrons to the party. When a phosphorus atom brings its 5 valence electrons to interact with silicon's 4 of those electrons bond perfectly with the silicon. But that 5th electron, it has absolutely nothing to bond with. It becomes a free-floating, unbound piece of extra electrical baggage just roaming around the crystal lattice. Because it is carrying this extra unbound electron, the impurity is known as a donor atom. It literally donates an extra electron to the system. This means that in an N-type semiconductor, it's the negatively charged free electrons that act as the majority charge carriers, completely taking over the job of conducting current. And thanks to this massive surplus of extra electrons, the energy dynamics shift in the exact opposite direction from our P-type. The Fermi level shifts way up to be near the conduction band. Because that energy difference is so small, very little energy is needed to push these free electrons into the conduction band to start rapidly conducting electrical current.
Now for the showdown, the head-to-head clash, P-type versus N-type.
The core difference really lies in the doping process itself. On one side, our P-type relies on trivalent impurities to create positive missing spaces, or holes. On the flip side, our N-type uses pentavalent impurities to supply an abundance of negative free electrons. When we compare the parameters side by side, we see an exact inversion. In a P-type material, holes are the majority carriers and electrons are the minority. But in an N-type material, it flips entirely. Electrons are the majority, and holes become the minority. They are perfect complementary opposites. If you're taking notes and only remember one crucial thing from this entire explainer, definitely make it this core concept. P fundamentally stands for positive semiconductors driven by holes, and N fundamentally stands for negative semiconductors driven by extra electrons.
Here is a thought to leave you with. On their own, these materials are super interesting, but when these simple P and N materials combine, they create the PN junctions that build everything from oscillators to transistors and LEDs. Just consider how these tiny doped crystals will continue to shape our future devices. Thank you so much for watching. Please don't forget to subscribe to Kognito Key and definitely like and share this explainer so we can keep making these for you. See you next time.